Uh,
All right. Hi, everyone. Welcome back. And for the second talk of today, we have Ben Elias, who is going to tell us about quantum geometric Satake and K-theory. Thanks, Ben. Take it away.
all right. Thanks very much. It's a great pleasure to be here in the Americas. So I'm going to be talking today about quantum geometric Satake and K-theory, which is joint work with Jordy Williamson. I also want to mention that next week I'll be talking about something related to the p-canonical basis and stuff. So my talk in the quantum symmetries session of the MCA may be of interest to people in this thing as well. What is geometric Satake? So geometric Satake is an equivalence of monoidal categories between two things, one of them really familiar and one of them pretty complicated and nasty. So the familiar thing is supposed to be representations of a complex semi-simple Lie group. On the flip side, you get some sort of category of equivariant perverse sheaves on the Langlands dual. That's what this check is supposed to be, the Langlands dual, affine Grassmannian. So for me, this is easy and this is hard. I never really understood the right-hand side of this. But given some hard work of Zergel and extensions of that by his student Hartrich, it's not actually hard to reformulate geometric Satake so that both sides are a little bit more approachable. In particular, so that this side is as algebraic as the other side. But I prefer to reformulate it as an equivalence not of monoidal categories, but of two categories. So I'll have to explain a little bit what the two categories are. But the first thing is going to be a sort of two categorical. It's basically the same thing as rep G, but spread out a little bit. However, I'll explain what this is on the next slide. I'm using the Lie algebra of G, representations of the Lie algebra, rather than representations of the Lie group. So if you know anything about the different groups that share the same Lie algebra, you sort of understand that, say, representations of PGL2 are just a subset of the representations of SL2 when you think about representations of the Lie algebras. And sort of this two categorical version encodes all of the different groups that have the same Lie algebra. You can encode them in one two category in sort of a fairly respectable way. On the other side, you got some two category of singular Zergel bimodules associated to this Langlands dual Lie algebra. So this formulation again gets rid of the choice of group with the given Lie algebra, but let's ignore that annoying point. So just as I remarked, this sort of version accounts for all groups with the same Lie algebra, and I claim that this side is much more straightforward than this stuff here, and so I will be able to explain what this side is in this talk. But first, I want to hint at it. So the input to defining Zergel bimodules and singular Zergel bimodules is a Coxeter system and a sort of choice of reflection representation of that Coxeter system. I guess you don't really need to equip it with roots and co-roots, but if you equip it with roots and co-roots, you have what we like to call a realization. And I'll mention that sort of realizations can be defined over any sort of commutative domain K. So a field of finite characteristic or a field of characteristic zero. The choice of K will be somewhat interesting in this talk. But so this is what we call a realization. It's just a Coxeter system with something that's like its reflection representation, like a Weil group acting on the Cartan. So one way to describe a realization, when the roots form a basis of this representation, then the co-roots are elements of the dual space, so they're linear functionals, and you can describe linear functionals by what they do to a basis. So the whole data is determined by how a co-root evaluates on a root. And you can encode this in a matrix, and this is called the Cartan matrix. And so, for instance, this matrix right here would encode for you a realization. This is the matrix of the Cartan matrix of the affine Weil group in type A. So this gives you a realization of the affine Weil group. And everything is an integer in sight, so you could choose your base ring to be the integers if you wanted, or any field. Any questions so far? So about 10 years ago, I made this very weird observation, and I kind of just pulled it out of nowhere. So you can Q-deform the affine Cartan matrix in type A. So if you take all the -1s on the off diagonals and you replace them with -q's and -q inverses, depending on whether you're above or below the diagonal instead of a cyclic way, then you end up with something that's still a Cartan matrix of a reflection representation of the affine wall group. It's a Q-deformed reflection representation. And moreover, this Q deformation was interesting. So if you use whatever construction you use to build Zergel bimodules from a realization, and you instead use this realization to build Zergel bimodules, then the right-hand side of geometric Satake is replaced with this Q deformation, and the left-hand side is actually replaced with our favorite Q deformation of representations of the Lie algebra, namely representations of the quantum group. Okay, so, in order to get this, that's why I invented this Q deformation. Again, it's a two-categorical version of it, but that I'll explain in a sec. And there's sort of two other caveats. So caveat number one is that this is only written up in the literature yet for small rank. It's true in higher rank, but sort of the technology to prove it is still like waiting for some other paper that one day Jordy and I will write. Very sad. The other caveat, which I've written small, is that the Q here is not the same thing as the Q here. I put a little invisible Q prime down here that maybe you can't see, maybe on purpose. But regardless, there's a relationship between them, and I don't care about this, okay? Okay. So when this appeared, there was no geometric explanation for where this Q deformation came from. It was just something I invented whole cloth to make the two sides match up. And it was also clear that you can't Q-deform the Cartan matrix in any other type other than affine type A. The point is that the affine Dingo diagram in type A is not simply connected, but every other affine Dingo diagram is simply connected. And that basically means that any deformation you might try, it just disappears by renormalization. This sort of raises the question, is this just a type A curiosity? Well, I mean, there are quantum groups in all types. You want to describe quantum groups in all types. You want there to be something in other types. It wasn't clear how to do it. But so finally in this talk, I'm going to explain to you at the end of the talk where this Q deformation comes from completely naturally, and how it, and you'll have already seen how it connects, it can be done in all types. So it is not a type A curiosity, and now I'm going to explain to you why. So first I want to explain to you what Zergel bimodules are, and more specifics about this construction. Any questions before I do?
Ben, so if you're restricted to finite type A, do you get anything interesting at all?
No. If you're so there's another version of this Q deformation, which actually this is not the original Q-deformed Cartan matrix I used in that paper. I originally used one that looked exactly like the finite Cartan matrix in finite type A, and only Q-deformed the affine part. If you ignore the affine part, you can just renormalize and it becomes the standard realization. Does that answer your question?
Mm-hmm.
Okay.
Thanks.
And I have a question too. Will you tell us what objects are in this two category?
Yes, very
Okay.
soon.
Okay.
You might have to wait a couple slides. So first I'm going to describe what Zergel bimodules are, and then I'll get to the two category business.
Cool, thanks.
Okay, so you have a realization, which is again just a representation of your Coxeter group where reflections act like reflections. And this gives you a ring, so the polynomial ring where the linear terms are that vector space. So like where the linear terms are roots, are spanned by the roots. And we give this the usual grading with gradings doubled, so that linear terms have degree 2. And I'm going to call that polynomial ring R. For any subset of the simple reflections, I'm going to let Wi denote the parabolic subgroup it generates. And I'm going to let R upper I denote the invariance inside the polynomial ring under that subgroup. So we're going to call a subset of simple reflections finitary if this parabolic subgroup is finite. It's annoying that you need a different adjective for the subset of the simple reflections because obviously all subsets will be finite. Okay, so the Shepard-Todd theorem and Chevalier theorem states this really nice fact, which is that if I is finitary, then in fact this invariant ring is not just some weird ring, but it's another polynomial ring. It has a bunch of algebraically independent generators. You in fact know what degrees they're in, and that R is a free module, a free graded module over this subring. This all fails if you don't choose a reflection representation or if it's not finite. I guess this may not fail if it's not finite, but this will fail if it's not finite. It will, sorry, I should have said free of finite rank. That will fail if it's not finite. It could be free of infinite rank. Now, de Mazur went one step further. I like to think of this as the upgraded Chevalier theorem. And he proved that, in fact, this ring extension is a graded Frobenius extension. So whenever you have an extension of rings, induction and restriction are adjoint to each other in one direction. But there's this other adjoint to restriction called co-induction, which is annoying. But for a Frobenius extension, induction and co-induction are isomorphic. So in fact, induction and restriction are biadjoint to each other, up to a grading shift. Co-induction is a grading shift of induction. And this is also true when you're including invariants under a small group, under a big group inside invariants under a small group. So induction and restriction, these functors of induction and restriction, which are biadjoint to each other, are realized by tensoring with bimodules, as all functors between module categories are. So induction is just tensoring with R viewed as a left R module and a right Ri module. And restriction is just the opposite, tensoring with R as a right R module and a left Ri module. But we're going to throw a grading shift into our definition of res so that the adjunction will work out nicely. And we're going to do something similarly to define ind and res between various invariant subgroups when one subset is contained inside the other. And so singular circle bimodules are a two category. The objects are going to be the subsets of S. And hum from I to J is going to be a collection of Ri, Rj bimodules. Actually, that would be hum from J to I, because that's how tensoring works. You tensor from right to left. So hum from J to I is the collection of Ri, Rj bimodules. And it's those bimodules you get by inducing from I to K, and then restricting from K to L, and inducing from L to M, and then eventually restricting or inducing to I. So everything you can get from iteratively inducing and restricting. So the tensor product says iterate that. You're also allowed to take direct sums, grading shifts, and the most complicated thing, direct summands. And by definition, this is the collection of all singular Zergel bimodules. Any questions about that definition? So I wanted to make a couple of remarks. Being a Frobenius extension is a structure, it's not a property. You need a choice of Frobenius trace or a choice of adjunction structure. And one way to spin this down is to pick sort of a trace map. This is a map from R down to the invariance. It's sort of some kind of symmetrization, but it's not, you can't use the symmetrization operator. You have to do something funkier. Such that there exist dual bases for this pairing. And when you pick roots and co-roots, that actually pins down this structure. So to give you an example of how that works, the map from R to RS, so RS is just the invariance under a single simple reflection. And the Frobenius trace map is called DS. And it can be given by this precise formula where you take the anti-symmetrization and you divide by the choice of root. So changing your root will change this operator. But another way of defining the operator is to observe that it actually agrees with the co-root on linear terms. It takes it takes linear things to constants. So it takes linear things to numbers. On linear things, it acts by an element of V dual. And then you can also extend it via twisted Leibniz rule. Roots and co-roots are related to each other. You can't just rescale one without rescaling the other. So the choice of roots / cos-roots pins down this operator. The choice of Frobenius structure, I'm mentioning this, it will play a role. It doesn't really affect the definition of the bimodules. The bimodules don't care. These bimodules are defined the way they're defined. They don't care about what the trace map is. It will affect the way that we sort of try to compute with this category and describe the category diagrammatically, which is important to some people in this audience. Okay, so now that I've said what singular zircle bimodules are, I can tell you geometric Satake. But G be a complex semi-simple Lie algebra. It's got a weight lattice and a root lattice. And their quotient is a finite abelian group. This is often called the fundamental group of the Lie algebra. So you're all familiar with the case of SL2. You've got even reps and odd reps. And for any irreducible representation, all of its weights are shifted from the highest weight by a root, by something in the root lattice. So all of its weights lie in a single coset. And that allows us to define the category rep sub chi for an element of omega, which are the representations whose weights lie inside this coset. So this 2 category is going to have objects equal to the elements of this group. So I'm thinking about to chi, I'm associating to chi the category rep chi. And one morphisms are going to be functors from rep chi to rep eta. And one way to get a functor is to tensor with a representation whose weight lives inside this category. Okay, so the Hom space is going to be this category. The Hom category is going to be this category, and morphisms are, of course, intertwiners of Lie algebra representation. So, for example, if you're doing the case of SL2, then the endomorphisms of the zero object are going to be representations whose weights are even. That's what rep 0 means. And so it's going to be representations of PGL2. If you want to get representations of SL2, you sort of need to look at a sum of Hom spaces. Both Hom from 0 to 1 and Hom from 1 to 1, for instance. Okay. So it's basically representation theory, only we're just keeping track of this small bit of extra data based on the group omega. But the group omega appears in a completely different way. I shouldn't say completely. So there's a natural bijection between omega and a subset of the affine Dinkin diagram. So it's those vertices you can remove to get the finite Dinkin diagram. So in SL2 tilde, you can remove either vertex, Z mod 2Z. For SLN, that's supposed to say SLN. You can remove any of these things and you'll get the finite Dinkin diagram. This gives you Z mod NZ. For say 2, the affine Dinkin diagram looks like this copy, and you can remove either of the outsides, but not the one in the middle. That gives you a finite thing, but not C2. And in type DN, you could remove any of the 4 outside pieces. Okay? To get the actual bijection between these things, you can think that sort of one of these is the affine node, and that corresponds to the trivial representation, or the 0 weight, which is the 0 element of omega. And all the other ones correspond to fundamental representations of the finite Dinkin diagram. And the fundamental representations will give you an enumeration of these cosets. Some of those fundamental weights.
Ben, the group for DN, is it a Z2 cross Z2 or?
It depends on the parity of N.
Oh, okay.
I'll also mention that like there's some Lingwens dual things going on here, and so it doesn't really matter whether you take the affine Dinkin diagram or the Lingwens dual of the affine Dinkin diagram. It's got the same removable vertices here. Okay, so I'm going to define this category here, S, on the other side of geometric Satake. It's got the same objects, So it's going to be omega, but interpreted as those subsets of the affine reflections for which the corresponding parabolic subgroup is the finite well group. So you can think about this as the affine reflections minus one of those removable vertices. Okay. And the Halm from I to j is going to be the category of singular circle bimodules for this copy of the finite well group and that copy of the finite well group. And so the theorem, geometric Satake theorem, basically tells you that this two category and this two category are equivalent. Now, that's a patent lie because representations of Lie algebra is not a graded category. Halm spaces are just vector spaces. This thing is a graded category. Halm spaces are graded by modules. There's all sorts of maps of non-zero degree. So the statement of this equivalence, and the reason I put a subscript 0 here, the statement is there's a functor, a two functor here, and that between any two objects in the image of this functor, there are no maps of negative degree, and that the maps of degree 0 are exactly hit by this functor. And then there's maps of positive degree that you just don't care about. Does that make sense? So that's sort of the geometric Satake theorem. And in fact, there's an understanding of these positive, if you want to understand what these positive degree morphisms correspond to over here, this goes under the name of derived geometric Satake. And you can, there's a whole lecture series at the IAS in the last year on YouTube that you can watch to learn about derived geometric Satake, but I won't bother to talk about it. Any questions about this? All right, so the theorem that I proved, again, in the literature, it's only in small rank, is that if you just use this Q-deformed reflection, you get a slightly different polynomial ring, with a different action of the same polynomial ring with a different action of the Weil group, if you will. That gives you a different version here. Over here, you've got the analogous two category for representations of the quantum group, and that you have the same exact state. Okay, so for the rest of the talk, I want to tell you a new perspective on this theorem. How much time do I have again?
Ten minutes.
You're telling,
I think
great.
10 minutes.
Okay, cool.
And Ben, you might have just said this, and I think that the Q, sorry, the Q's that you have there before, you were like, there's a Q and there's the UQ, and it's not quite the same Q. Is there the same thing happening here?
Yeah, same thing here. Yeah.
Okay.
Ben,
Okay.
what are the Qs? Are generic things or root of unity?
Yeah. I forgot to mention it, but I'm defining my base field to be ZQQ inverse.
Okay.
You can get, so if you set Q to be a root of unity, something extremely interesting happens, and I can talk about that later.
Yeah, great.
Okay. So the word new should be applied to things later in this slide, not to this part. So all the structure that's entering this construction of singular circle bimodules when W is a crystallographic Coxeter group has a geometric origin. So this polynomial ring is just the B equivariant cohomology of a point where B is the Borel. Or the Borel of the affine Kac-Moody group if we're doing affine stuff. The invariant subring is the P equivariant cohomology of a point for the corresponding parabolic subgroup. This Frobenius map is the push forward, and the inclusion map is the pullback in cohomology. And all this structure can be described geometrically. So instead of saying that the input to defining circle bimodules is a Coxeter system and a realization, in the cases where this comes from geometry, I could say that the input is a Coxeter system, sort of a particular geometric setup, and the ability to take equivariant cohomology. So sort of the new perspective is, what if you just instead use some other equivariant homology theory, generalized homology theory? And instead, in this talk, we'll use K theory, equivariant K theory. I'll remind you about equivariant K theory in a sec. But so what if we just use the K theory version of R. We just use the K equivalent, the B equivalent K theory of a point and the P equivalent K theory of a point and the corresponding pull back and push forward maps there. What do we end up with? Can you repeat this whole story? You can repeat the whole story. This is still a Frobenius extension. You have induction and restriction. There's nothing wrong. You can exactly repeat all the definitions before. These are just rings, inclusions of rings, Frobenius extensions, no problem. And you get what are called K-theoretic Zergel bimodules. This is sort of a new thing that is being studied now by Jordi and I. To contrast them, we're going to call the original ones homology Zergel bimodules. So just to give you some compare and contrast, so suppose we're doing SL2. We've got the reflection representation, which is one-dimensional, and it's spanned by the root alpha s, and S of alpha s is minus alpha s. And so the polynomial ring is just a polynomial ring in one variable. Okay? It also sort of, if the fundamental weight in this case is alpha s over 2, and so long as we're working over a base ring where you can divide by 2, you can also think about this as the polynomial ring in the fundamental ring. Meanwhile, K-theory depends on a choice. It depends on a choice of lattice. So RK is the group algebra of a lattice with a W action, but you need to choose which lattice you're doing. You get two different answers if you choose different lattices. So if you're working with the root lattice, you should think that when you're doing group algebras of a billion groups, you usually use exponentials. So instead of alpha s, our generator is e to the alpha s. And the group algebra of that is the group algebra of Z is ZYY inverse. If I had used the fundamental weight, I should let x be e to the omega s, which is the square root of y, and look at zxx inverse. So these are slightly different rings. I mean, they're isomorphic, but one includes inside the other. But the difference here is that when you act by s, it sends e to the alpha s to e to the minus alpha s. It sends y to y inverse. That's very different from sending something to minus itself. You send it to its inverse. It's a very different ring structure. Sorry, very different action on this ring. So for SL3, for instance, S of alpha t is alpha s plus alpha t, whereas here everything is done exponentially. So S of e to the alpha t is e to the alpha s plus alpha t, which is e to the alpha s times alpha t. So plus becomes times. Before the de Mazur operator, I gave you this formula, and you can sort of check that the ds of alpha s is 2, ds of alpha t is -1, and so forth. Whereas the formula in K-theory for the de Mazur operator is a little bit more annoying. So for instance, here are some values of ds. Just to give you a flavor of what's going on here. So, so here's the theorem which we verified in types A1 and A2 and C2. And it's important that we did C2 because it's not simply connected, and that's where we couldn't do anything before. We'll conjecture it in general type. And the statement is that actually, if you do the K-theoretic version, then what this is equivalent to is representations of the quantum group. Now I have to explain a couple things about this. There's like 10 caveats I have to say. All of them are sort of important. So first I'll say we prove this directly by generators and relations in similar to fashion to how I proved the previous theorem. So first off, what is Q? So there's no Q here in K-theory, except that if we're working in affine type, there's this imaginary root. It's W invariant. And so you can think about it as being basically a scalar. You can move it to your base ring. So e to the delta, e to the imaginary root is now Q squared. Okay, so that's what Q is. And so the first caveat is that this ring, RK, is not a graded ring. Or I guess you could make it a graded ring, but the action of W is not homogeneous, so who cares about the grading? However, it is a filtered ring, and this associated graded is homology. So this is the general thing about K-theory. Comes equipped to the filtration, the associated graded is homology. You can actually, filtration is the category of Zergel bimodules. So you can sort of define filtrations on the bimodules themselves, and that gives you a notion of filtrations on the maps. And the associated gradient of this category is that rate, and Q goes to 1. In fact, e to the lambda goes to 1 for all lambda. So, so you could look at filtered degree 0 maps, or like, modulo filtered degree 1 maps, and that's what this this is supposed to mean. Like, so it's an equivalence to degree 0. It no longer makes sense, but it's an equivalence to filtered degree 0 in some sense. So you have to take that equivalence to degree 0 with a grain of salt, but it's easy to reformulate. So the second statement is that, is this really a geometric reformulation of what's been done? Well, so normal Zirkel bimodules are equivariant global sections of perverse sheaves, so they have like a really concrete geometric meaning. There's no such thing yet as K-theoretic perverse sheaves, so it's hard to say what these are the global sections of. We'll leave that point aside. One day there will be geometry to explain this, but at the moment it's not really geometric. It's just a different kind of algebra. Also, the higher degree maps should be described. Kautas-Kamnitzer basically kind of did this in type A, although it's a different way of constructing it. So it should be, if you understand sort of all maps, not just filtered degree 0, the work of Kautas-Kamnitzer kind of tells you what to do in type A. It doesn't tell you what to do in type C. It's the same, it should be the same idea. It tells you what to do, it just doesn't prove it. Okay, so the third caveat is a weird surprise, super weird, which is that we use the Langlands dual of the affine rather than the affine of the Langlands dual. So in type C, for instance, C2 tilde has this Cartan matrix and this Dinkin diagram. We actually, to match up with the quantum group, we actually need this Dinkin diagram, which is not an affine Dinkin diagram at all. It's the Langlands dual of the affine type. And you can do this explicit computation where you compute the dimension of the standard representation for these two different versions of K-theory. And in one, you get quantum dimension minus quantum 4, which is incorrect. And for this one, you get quantum dimension quantum 5 minus 1, which is correct. Probably this has to do with some hidden causal duality that's behind the story. The next caveat is that we also need to choose our lattice very carefully. If Q squared the delta, we better need either the delta over 2 if we want to have Q. Which means that we need some lattice which is sort of bigger than the usual root lattice. Sometimes we even need some weird stuff. And so I can describe what this lattice is, but it's kind of just a weird thing about working with K-theory that confused us for a hell of a long time. So I wanted to conclude in the last minute or so by explaining the relationship to what I started the talk with, which is this Q-deform Cartan matrix. So first I'm going to start with a finite type A version of this. So in type A, if you don't work with SLN, but work with GLN, it's really important to work with GLN, something interesting happens. So the normal polynomial ring is a polynomial ring in n variables permuted in the usual way. The K-theory ring is a Laurent polynomial ring in n variables permuted in the usual way. And a Laurent polynomial ring has a polynomial subring inside it. So effectively, this is because the lattice actually has a sub, an orthant inside it, a quadrant is preserved by W. That doesn't happen for SLN. Okay, so that gives us this polynomial subring. And so we can think about, let me just skip ahead. So this polynomial subring and this are just completely isomorphic as a W module and everything. So the K-theory Zirkel bimodules are just bimodules for this thing, but then you localize your variables. So there's no difference between K-theoretic Zirkel bimodules and just ordinary homology Zirkel bimodules where you localize some, where you invert some variables in type A for GLN. Of course, this doesn't preserve roots and co-roots, and your de Mazur operators are different, so that you got different diagrammatics, but it's the same category. So in affine GLN, you can do something similar. Sort of, there is a version, I'm not going to go through the details because I'm out of time, but there's a version of this sort of reflection representation of the for a GLN version of the affine reflection representation with some formula. And if you do a theory version of that, you exactly get the GLN version of my Q-deformed Cartan matrix. So the statement is that actually, so again, there's some sort of thing that's almost like an orthant that's preserved by W inside. It just has the imaginary root needing, you need the whole copy, you need the whole integers there. And so K-theoretic Zirkel bimodules is just the localized version of the Q-deformed Zirkel bimodules. So that relates the new theorem with the old theorem. Okay, sorry about going too fast at the end. There, I've done it.
Thank you so much, Ben. That was really, really great. Can we please thank our speaker? Does anyone have any questions for Ben?
I have a question. This is Chuck Weibel.
Hi.
When you talk about the quantum things, there's usually a Hopf algebra structure going on. I didn't see anything about a Hopf algebra structure in your talk. Is it there or just not known yet?
Yeah, so I mean, what the Hopf algebra structure gives you is tensor products and duals. That's all there. You know, this is a two-category thing, which sort of is like monoidal, right? So it preserves the monoidal structure. It preserves duals. What is sort of not obvious is the braiding. Most people care a lot about the braiding, and that's what's interesting about the quantum group in some sense. And this is a very subtle thing, which I can talk about in some length, but probably not right now. There is a braiding that essentially Lustig defines that should work in this Q deformation as well. It won't match the standard conventions for the braiding in representation theory, but actually it's probably the correct braiding.
Any other questions?
I have a question.
In geometry, can I ask a question? Yeah, sorry. So in geometry, so can you take like K-theory of Bot-Samuelson varieties and things like this, and like start building morphisms within Zorgil bimodules? And
right,
lightly use as
right. I mean, so like even in homology, describing morphisms using homology is kind of funky. But I mean, yes, you can do it. And do you describe the morphisms using K-theory this way? I don't really know. You can certainly, there is a diagrammatics for morphisms that we're developing. It's basically the same as the old diagrammatics. Again, the associated graded agrees with the original. So the answer is probably, the question is almost certainly yes, but I don't think of it that way.
Mm-hmm.
So this is what Kadas-Kamnitzer effectively do. Kadas-Kamnitzer say that when everything is minuscule, there's sort of nice features of the geometry that say that Hom spaces should just be understood with K-theory of certain geometric spaces. And they describe all the Hom spaces that way. But this doesn't only works when your geometry is nice enough. So Kadas-Kamnitzer basically do what you suggest. It just doesn't always work.
Yes. I think I was thinking about finite type A even. So in finite type A, you can say, well, so you have Bot-Samuelson varieties, you have all this stuff, and then you have homologies.
Yeah, it'll probably
K-theory
work
of
there.
that.
It'll almost certainly work there, especially since, I mean, finite type A K-theory really is just localized homology, and this is true in geometry as well as in the category of Zirkel bimodules. In finite type A. Yes, Nico.
I have two questions. One is kind of vague, but so your theorem from 2014, it's not like it's kind of it's a conjecture essentially in general.
Yeah, because I didn't write down the type. I have done enough computations that I know how to prove the general case, but there's not enough.
Okay.
There's not enough literature about singular Zirkel bimodules and diagrammatics for me to actually prove it. So let's call it a conjecture.
Okay, but you know how to, and this one, it's kind of a similar situation that you need more literature to prove it. You kind of
Right.
know.
So because of this statement here, that like proving the K-theoretic equivalent in type A, and is this equivalent to proving this earlier theorem that I in
I
type
see.
A. So they really are the same statement.
Okay.
But in general, like I have no idea how to prove this in general.
And my second question is, so you have you thought about this? You mentioned this causal duality that there might be here. Do you know more or less like it would be something similar to the circle by module, the homology circle modules causal duality?
Right. I can't say that I really know enough about it, right? I mean, these are slightly different rings, so causal duality is different. But presumably, this is the explanation for what's going on. Like via AMRW and something. That's probably why we end up with Langlands duals of affine type. I really don't know any details. I haven't thought hard enough about that yet.
Ben, so I have a question. What's the abbreviation on your first slide?
The abbreviation on my first slide, so now I can get there fast, give me a sec, is, I believe, and you'll have to tell me, categorification, higher representation. What's the name of this?
Oh, I see. This is the special section. I see. Yeah, homology theories are not maybe okay. And can you, is there just not, my real question, is there just not a K-theoretic version of SLN of type A circle by modules with the SLN?
Oh, absolutely. There's a version for K-theory, and yeah, but it's not a localization of homology.
So do you get some, okay, so can you, I don't know, can you repeat the process of like computing or like defining the von Horizontal homology to get something interesting? Or is it?
I mean, so Rouquier complexes still work all the same way they used to. I see no reason why not. Now I haven't like, so Rouquier complexes still work. So that I don't know about the Markov move.
Yeah.
But that gives you, Reidemeister 2, Reidemeister 3.
So okay, but if you did have a Lincoln variant, would it be like genuinely new, or would it be?
Right, everything's finite type A. Now the map. Okay, so let me tell you this, right? Like, how many Rouquier complexes could you define for a single crossing? Your differential is a dot. I guess you could rescale the dot, but that does nothing up to isomorphism. Now you can rescale the dot by a whole ton of things, because there's a lot of invertible elements in K-theory. Of course, they're all the same up to isomorphism still. But what I'm trying to say is that the canonical choice, like the dot map that you get from the Frobenius structures, is different. Like ultimately, probably that doesn't affect anything, but I don't know if it does. Probably not. I bet it's the same.
Okay.
All right. I think this is a good spot to thank our speaker again. You're welcome to stay and ask some questions, but we can end the recording here. Thank you, Ben.